I'm Anthony Francis. I've been a Googler for a couple of years, and originally at Georgia Tech. And Ashwin Ram is not only my thesis advisor, he's an international expert on case-based reasoning, natural language understanding, as applied to a whole variety of areas, including information retrieval and game artificial intelligence. And today he's going to talk about case-based reasoning for game AI. So.
Thank you, Anthony. So it's a pleasure to be here. We're going to keep this informal. If you have questions as I go, raise your hand, stop me, we'll talk. My lab at Georgia Tech is called the Cognitive Computing Lab. And this work is done with a number of collaborators. People shown in red are people who are currently in my group, but you'll see some papers by people shown in blue as well. I've turned into a pointy-haired boss, I think. I have all these students doing cool stuff. More work with few people. OK, so what is game AI? When you talk about game AI, most people conjure up an image like this in their mind, right? There's some kind of a game. This one is Wargus. It's a clone of Warcraft 2. My teenager tells me I'm outdated because now he's playing World of Warcraft, and this is a couple generations old. But it's actually, strategically, it's very much the same game. In this game, you have, of course, the two armies. The black area here is the fog of war. You don't necessarily know where everybody is if you haven't explored. And you kind of think of game AI as this engine that is going to craft a strategy for you. So in this case, we're going to build a base, set up resource infrastructure, production infrastructure, a base defense, build towers, et cetera. And so AI is this thing that's going to crank this plan out for you. But both the notion of game and the notion of AI is much broader than that. And what I'd like to do today is give you an overview of some of the kinds of things we are working on in our group. Happy to dig into details of any project or any techniques that you're interested in. So to begin looking at what game AI might be, let's start with what games are. So we're also familiar with the notion of games as entertainment, right? New era technology and creativity will fuse to produce stunning entertainment. But games are a lot more than that. Games are being widely used as educational tools. I particularly like this quote because it's from The Economist. It's really coming from the business community. Games are being used in management and leadership training. These are called Serious Games. You've probably heard of the Serious Games Initiative. There's their website. And they're really being used to engage the country in a dialogue about challenges in the public sector, in education, in governance, city planning, health, and so forth. Games, of course, there's also social games or humane games, which are interactive games that are designed to engage people in humane or social causes. So why games, right? Why am I working on games? Why should people be interested in working on games? Well, games clearly are relevant. We have all these kinds of games. Games are hot. These statistics are actually a couple years old. The game industry and the movie industry go neck and neck. One beats the other by $1 billion or $2 billion any given year. But roughly speaking, there are about 2 games a household. Any given time when you survey people, about a little under half the people are sort of in the immediate market for a game. So it's a pretty large and engaging industry. So what games are people buying? People know what are sort of the top-selling computer games? Any guesses? Visual. Yeah. Here's a hint, or some hints. Right? That's Sims. People know this one? This is one of the top 5 games. Roller Coaster Tycoon. So these are some of the ones. There's actually a couple new ones now that are starting to make the charts. World of Warcraft, The Sims. What's interesting is it's a very wide range of things, from things like simulation games to really just hardcore battle games. The nerdy teenager games, if you will. Okay. So games are this hot thing. They're pretty broad. Games appeal to a very broad segment of society. And as academics, and especially in AI, a lot of us have tended to work on fairly esoteric problems. We work on robotics, and we work on expert systems and things that are of interest to, sort of important, but of interest to niche groups. Games, on the other hand, have a very, very wide appeal. In fact, there's some really interesting statistics put out by the Electronic Software Association, the Entertainment Software Education. People know what the average game player age is? This is surveys of people who call themselves gamers. So they're not people who play a game once in a while.
36, 35.
Yeah, close, 33, right, 33. In fact, they're pretty interesting statistics. 25% over 50. Any parents in the audience? A third of us are playing games. I don't know where they find the time. I don't. About half of them are moms. Right. This one is relevant for this year. What percentage of gamers vote? Any guesses? Are they sort of nerdy, dysfunctional kids who don't give a damn, or these serious, engaged citizens? It's surprisingly high, 73%. In fact, if you look at the statistics, and I must caution you, this is put out by the ESA. They want us to believe that games are played by regular people. But fairly some engaged type of people. They're playing sports, they read, they attend theater. Yeah? I think of eligible gamers.
Okay.
Yes, yeah, that's a good point. Okay, but basically these are regular people, is the point, right? So games appeal to a wide range of regular average people. From my perspective, the most interesting thing about games is that games are AI complete. Okay, what I mean by that is if you look at what it takes to be good at games, right? Here are some quotes from that same Economist article. Players must construct hypotheses, solve problems, develop strategies, learn rules, juggle tasks, right? Good game players do all of these things. Well, if our AI systems are going to play at games at human level, they have to do all of these things as well. These are all unsolved problems in AI. So games are AI complete in the sense that developing human-level game AI requires you to solve all of AI. And of course, we're going to try to make a dent in that. Okay. So the kinds of games that I'm working with, there's games like Wargus. This one's called Mad RTS. They're real-time strategy games. I'm sure you've seen them. And let me see if I can get this thing opened. Okay, so here's kind of a clip from this game. And basically we have blue troops is us, red is the enemy, and we're playing the enemy here. If you notice, the enemy is starting to bunch up and attack, whereas we're spreading out trying to engulf them. Turns out this is a very good strategy here. So the blue is a game AI system playing prior to any kind of learning going on. And in this case, the red strategy, which is a human player, overwhelms the blue and wins the game in a few more seconds. So that's kind of an example of Wargus or other type of game, Battlefield 2 type game. And we're doing a bunch of work in my group with games like this, looking at how game AI systems can not just play these games, but learn how to play these games better by learning strategy. Okay. We also have interactive fiction. These are some of the popular interactive fiction games you've probably seen. They're often not even called games. Interactive narrative might be a better term. Here's an example of one that my student Manish Mehta worked on in Denmark. This is a simulation of Hans Christian Andersen. It's a museum. In the museum setting, kids go up and talk to this character through video.
Hello, how are you?
Show you a short clip.
Hello, glad to meet you. Do come in and let us talk. It is a pleasure that you come visit me in my study. Before we talk about other things, I would like to know about you. I cannot see.
And it goes on. So basically, it's sort of an interactive character that you can talk with. This particular one is targeted towards kids and youngsters. You can also visit various fairy tale lands that they've created. You speak through speech and touch. And there's this sort of animated embodied characters. Okay. So that's another kind of game domain that we're dealing with. So when you start working on creating characters like this, or even strategic games, game players that play games like this, one of the first questions that arises is how are we going to represent strategies, personalities, goals, actions, et cetera? We need a language for doing that. The formalism we're using is called ABLE. It stands for a behavior language. It was introduced by Matthias and Stern at Carnegie Mellon. It is a programming language. I'll show you some examples of it, but it's a programming language that allows you to implement sequential and parallel behaviors, goals for individuals as well as teams of agents. It implements joint intentionality framework, sort of similar to Mill and Tombes, if you're familiar with that work from USC. You can have reflection behaviors that reflect upon behaviors. There's a sensory motor abstraction, et cetera. Here's sort of some here's some example of able code. That's a parallel behavior where to attack the enemy, there are these two sub-goals you have to execute in parallel. Here's a sequential behavior. There's a set of preconditions that trigger the behavior and then something you do at the end, and so forth. So it's sort of this production system, C-like syntax. Okay. So given that we have this language, where does the AI go? Well, one obvious place for game AI is in the non-playing characters. So we can have, you can be playing Wargus and fighting against an AI enemy, or you could be interacting with Hans Christian Andersen with AI powering the character you're interacting with. So this is what's called character level AI. We have believable agents with complicated behaviors that are programmed using some kind of AI programming language. The AI is focused on achieving the NPC's goals. There's another kind of AI which is at the director level. Okay. So this in interactive narrative is often called the drama manager. So think of it as the game designer or the author of the game has certain affective and narrative goals in mind. They want to engage you in a particular way. The job of the drama manager or the director level AI is to watch over your interaction with the game and try to manage the game, manage the interaction to achieve the author's rhetorical goals. So for example, if you're trying to educate somebody, we might change the game a little bit on the fly to make it more educational or more entertaining or more whatever the purpose is. So the objective there is to enhance the player experience, not to pursue the goals of any particular NPC. Okay. So why is this hard? If you look at these types of games, the state space, the decision space is massive. In fact, there's a nice paper by David Aha and his colleagues in ICCBR a couple years ago that shows that it's basically undecidable. Thousands of actions are possible. The state space, the perceptual space is very, very large. Games are non-deterministic. If you're familiar with AI planning, classical AI planning, for example, strips, NOAA, et cetera, you have these operators that define what agents can do. They have a set of preconditions that trigger them and a set of postconditions, results that entail when you execute those operators. If you unlock a door, the door is then unlocked. Well, it turns out in game domains, you can't write postconditions, because what happens when you pursue a strategy depends on what the opponent is doing and a mass of other things that are not under your control. So right, it gets very, very complicated. The games are non-deterministic, and things happen in real time you have to adapt to. If you look at the games like the ones I've showed you or shown you or several others, if you look at sort of this code that you're writing, the hard part really comes from two perspectives. The theory is hard. How do we model realistic human-level behaviors, goals, personalities, emotions, interpersonal relationships, strategies? Right? We don't know theory. AI and cognitive science isn't advanced enough to capture all of this yet. And this is kind of what makes it interesting for me as a researcher to tackle the game AI problem. There's also an engineering problem. Hans Christian Andersen, if you look at the effort that went into building this museum exhibit, the AI was much larger, really, than the rest of the game put together. In part, that's because they're very good tools, graphics engines, speech engines, et cetera, whereas for AI, it has to be crafted from scratch. That's one character. Facade, people heard of Facade? So Facade won the Slam Dance award last year, 2 years ago. It was Michael Matthias's game. It's an interactive version of, if you've seen or heard of Who's Afraid of Virginia Woolf, the play by the famous American playwright Edward Albee. You get invited to this couple's house for dinner. The couple's bickering, the marriage is on the rocks, and you sort of play the play with the characters. The characters are scripted using ABLE code, but what happens and what they say and what they do and how the evening goes depends on what you do. You can interact with them in natural language, or more recently through an augmented reality headset. So it's like an immersive theater-going experience. That has over 200,000 lines of able code for 2 non-player characters, the husband and the wife. Okay, that's not scalable. It's a lot of effort required to craft all of these characters and all of the behaviors, goals, personalities, et cetera, that you're going to need. Okay, so that's partly what makes this hard. So we can't engineer the game AI. There's too much knowledge to program in. And your users, the kids in this museum, are going to come in and say something or do something that you didn't anticipate. The world's going to be different. Right? You can't learn everything by trial and error either. You can't just throw machine learning at it because the state spaces are too large. This says genetic engineering got us into this mess, and genetic engineering will get us out of it. Okay, this isn't a reinforcement learning problem where you can run thousands or millions of trials and somehow the game AI will train itself. You really need a combination. Okay. So the 3 key ideas that I've pushed in my research are asynchronous reasoning and learning, goal-driven learning, and case-based reasoning. I'll touch on each one in turn, and I'll give you some examples of them. So the asynchronous reasoning and learning idea is this. If you look at, again, traditional AI, you have systems that work in one of 2 ways. So classical AI, you build systems that reason, they solve problems, and then they analyze what they did to try to learn from that experience. Explanation-based learning works this way. In machine learning, it's sort of the reverse. You take a learning system that is empty in some sense, and you train it using tons and tons of data. And when it's ready, then it's ready to solve problems. So the asynchronous reasoning and learning idea is that you have to do all of these things simultaneously. Perception, reasoning, action, adaptation, and learning all must happen continuously and in all the time and sort of online manner. You can't separate the 2. So that's one theme that goes through most of my work. Second theme is goal-driven learning. Again, going back to traditional machine learning systems, the human researcher or the application engineer decides what the system needs to learn, what algorithms to use, what training data to provide it, and the system sort of crunches the numbers for you. The goal-driven learning idea is that the system itself has to decide for itself what it needs to learn, even whether it should learn. There's too much to learn everything. What should it focus attention on? When should it learn? What kinds of algorithms to use? And this requires meta-reasoning or reflection. This requires the system to think about and look at its own traces and figure out what went wrong, what it needs to improve. And there's a book that I've edited with David Leake, which a collection of papers on this topic. Okay. And the third key idea is case-based reasoning. Again, going back to this sort of dichotomy between GoFi, what's called good old-fashioned AI, and statistical machine learning. Is it knowledge-based or is it statistical? The case-based reasoning really pushes the idea that it's not an or, it's an and. It's both of them, right? And these are some of the authors you probably recognize in this area if you know CBR. The basic idea is that we have this repertoire of experiences that an agent has. Agent might be you or I. It might be a computer agent. It remembers what it knows, brings it to bear on a new problem, and then tries to learn from that experience for next time, learn a lesson. So it is learning from experience in that sense. It is incremental, empirical, statistical, but it's happening in a lazy manner. It's happening as you have the experiences, not trying to pre-train the agent all up front. So those are some of the ideas. This is sort of a snapshot of the architectures that we're building. We have an agent that gets in a set of goals. It has a set of actions, strategies, personalities, behaviors available to it. There's a planner that looks at the state of the world and so decides what to do next. The execution agent then sends back actions, watches what happens. The learner is sort of watching the state of the world and the trace of the execution, and so updating the action library or the behavior library. And all of this is all happening at the same time. So the actions available to the planner might be changing out from under the planner as it's using them to plan. And the planner then has to decide whether to replan or keep going or whatever. In fact, it gets more complicated. We have stacks of these things. We want to have a range of asynchronous reasoning and learning agents all the way down from the primitive action level where we're just selecting the next action to perform all the way up towards planning with strategies and tactics, and even up to drama management, looking at the whole evolution of the game and deciding if the game is going in the right direction. And each of these is an AI problem in itself. I have students working at several of these levels. Let me give you a sort of taste of some of these projects. So at the lowest most level, and I'll show you some sort of citations here if you're interested. Papers on my website, or you can send me email. I'll be happy to send them for you, to you. But so the idea at the action selection level is we have this large state space that we've captured, we've perceived in some manner. We're going to try to find actions in our past that were performed under these circumstances that did well for us by some metric. And so here's, in abstract terms, here's the point we're at along some dimensional space. We're going to find a few nearest neighbors that are our past experiences, and from them try to decide what we want to do next. So this is the most statistical and machine learning style layer in the architecture. And this is how it works. Let me just show you a picture of that same scenario I showed you earlier. This is after learning. So we're going to play the same game again. We are blue again. Enemy starts to bunch up as it did before. We've gotten a little bit smarter, and we're starting to bunch up as well and penetrate the enemy. There's a bunch of exchange of fire, but we're staying clumped up together instead of trying to go all the way around like we did earlier. And it turns out we are able to defeat that clumped up group over there, and after that it's pretty easy to wipe out all the stragglers. So the interesting thing is the system got to this point, learned the strategy for doing this purely autonomously. I didn't have to program it. Okay, and that's where the case-based reasoning comes in. So that's at the lowest level. At a tactical level, we can use a similar technique to select tactics rather than just actions. So here are a couple of examples from other researchers who are doing this. This is David Aha's work at the Naval Research Lab. You have a description of the state space, a set of tactics available to the system, and the system remembers these cases, which are essentially tuples of a state description and a tactic that was performed and what actually happened. The system can use this to learn which tactics to select under which situation. Ponson and Spronk have a similar approach. They call it dynamic scripting. Instead of picking a particular tactic, they're picking sequences of actions or sequences of tactics. They call them rules that need to be performed one after the other. So in this case, we're going to build a town hall and a barracks by building a lumber mill, chopping more wood, et cetera. This whole sequence gets learned through experience. Okay. I've done some work in this area in a robotics type domain as well. This is work with Juan Santamaria, one of your fellow students many years ago. And here the idea is that we keep a track, a time history of sensory readings or perceptions from the world as we are playing it, from the game world as we are playing it, as well as a sequence of actions that were performed. And the system then learns patterns over this to recognize that when I'm in a certain type of situation, I can find a similar matching pattern that looks a little bit like what I'm seeing right now, and from that, decide what to do next. This type of approach ends up learning tactical knowledge because it extends over short periods of time. So the system learns, for example, that if I'm entering a very heavily crowded environment, I might want to slow down, or I might bump into something or get ambushed. The system can learn those kinds of tactics autonomously. When you move up a level, I took this slide from Anthony's PhD thesis work. This is a snapshot of a planner. When you move up a level to a strategic level, now we're getting away from just looking at numerical values over time and looking at strategic planning type issues. So here we have to reason about goals and strategies and plans and counter plans and so forth. So what the system is doing here is search in the space of partial plans. There's a paper that I did with Anthony Francis on this. The system then remembers partial plans from its past experiences and splices them together to create plans for the new problem. So what we've done here with Vargas is extend this idea to real-time domains. The system has this goal to win the game. It's currently considering a plan which involves pursuing goal 1, followed by goal 2 and 3 in parallel, followed by goal 4. Goal 1 has been expanded into a sequence of actions using a case base, which tells it what to do for goal 1. But unlike a traditional AI planner, we haven't yet planned what we're going to do for goals 2, 3, or 4. We don't know what this world is going to be when we get there. right? And that's sort of the difference. Because we cannot predict the outcomes of our actions, we just have to execute them, see what happens. So this gets close to actually one of Charlie Merton's colleague, Jim Furby's work on RAPs, reactive action packages, which is a way of doing planning in a reactive or unpredictable space. So in this case, we're going to build this plan, but delay adapting the plan and expanding it until we get to that point in the game. And there's some papers about this kind of delayed adaptation techniques as well. Okay. Another project we're working on is sort of learning these case libraries. If you're going to watch an expert play, either because he or she is demonstrating it to you or because you're just playing somebody who's better than you are, what the system does here is sort of looks at the trace of the game as it progresses, and from that tries to capture little snippets that can be stored away as cases. System doesn't actually know if the cases will always apply. The details might be different, but it's a starting point. And when the system then goes to play the game, if it sees something that is sort of like the situation that is seen with the past, it will then remember this trace and try to adapt it and work on it and try to learn its applicability conditions. We've done some experiments with this. We go on to, my students love this part, we play lots of games on BattleNet, which is for people who are into games. It's a popular, I guess, a portal for human players. There are a bunch of these maps that are highly strategic in nature. This one's called Nowhere to Run, Nowhere to Hide. And computer systems are typically poor at playing these types of strategic maps. These are very popular maps among human experts. They tend to, and there's sort of variations of them. What we do is we train our systems to play these types of maps by playing them against experts or our own students and seeing how they get better over time. And I won't go into the experiments in detail, but just roughly speaking, the system is sort of this is with learning versus without learning, getting better over time as it plays against, in this case, one of my students. Okay, now we jump up a level. So thus far, we had these systems that were focused on sort of achieving the goal of the game. A lot of this work has been done in these real-time strategy games. Now I'll show you a couple of projects looking at the authorial goals or the rhetorical goals of the designers of the games. This is a game that was built on top of Unreal Tournament. It's a game of tag intended for kids. You go in, and these are characters with different personalities. You go in and play tag with these characters. And in this case, that's Jill. She's very aggressive. She likes to taunt the other players. And Jack is somewhat more shy. He gets frustrated very easily and gives up if he's not having fun. And so forth. There's a series of characters you can play against. So the problem we're trying to tackle here is that the people who created these characters didn't get them quite right. If you try to create one of these characters using Able, for example, Jack may not be quite as easily frustrated as you as a designer might have liked him to be, right? So what we do is we have Jack or Jill or whoever display these games look back over what's going on in the game and say, hey, my designer intended me to be this kind of personality. It's not really coming across. Can I tweak my own behaviors and be more like what I was intended to be? So we're getting now into this drama management director level AI where using meta reasoning, we can have the games sort of fix themselves. So if you build a game like Facade, which hundreds of thousands of lines of code, and these characters are not quite what you intended, they can oftentimes fix themselves, or at least help you fix them. So it's sort of, think of it as automatic programming, if you will. And we have some papers describing that this work as well. So here's sort of an example of how this works. We start with this behavior library and this semi-reactive agent. The agent performs a set of actions in the world. It could be a real-time strategy game, could be an interactive drama type world. It's a non-deterministic world, lots of exogenous events. System tracks what's going on. We call that the runtime trace. Detects anomalies, detects things that aren't quite going the way you intended them to be, and then identifies rules that let it go in and tweak its own behaviors. These are code rewrite rules. System matches those into the traces, fixes the behaviors, reinserts them back into the behavior library. We had fun Java, trying to get Java to reinsert running code and have it keep going. We wish we had done this in Lisp. be easy to hand that back to an eval. But anyway, reinsert that back into the running agent and so forth. We've also looked at what's called player preference modeling using drama management. The goal here is to not to change the game, but to gently guide the player towards more enjoyable parts of the game. So we have the game engine here that's interacting with the player, and the game engine is generating a trace that is fed to a player modeling engine that then is used by the drama manager to decide how to interject actions into the game. Here's an example from Anchorhead. This is a very popular interactive drama. We've put a 2D interface. This is a text-based game where it's a classic adventure game, Zork-type game. You type to it in so there's broken English, and the system then tells you what's going on in the world. We've put a 2D interface on this. And so in this example, as you enter this room, the player, in this example, the system has figured out that you're a novice player and is giving you a hint, drawing your attention to an artifact that you might otherwise overlook. If you're an expert player, the system might decide to lock the door and have you hunt for a key, because finding the locket too early in the game makes it too easy. The system figures that out itself. We run studies with human subjects showing that with the drama manager turned on, people tend to enjoy playing the game a lot more. So we're not measuring sort of success in the game in terms of defeating anybody, but just in terms of enjoyment of the players. Okay, so let me get back to this sort of vision of this architecture. We have these multiple levels of reasoning. So roughly speaking, goal-driven learning comes in as each layer directs the layer below it towards certain learning objectives. So the meta reasoner tells the strategic layer what to learn. A strategic layer is telling the tactical layer what to learn, and so forth. And that helps guide the learning process. Down at the bottom, we have this reactive execution, where, again, you're trying to execute based on the knowledge you have, never quite sure what the world's going to throw back at you. And that's where the asynchronous reasoning learning comes in. Case-based reasoning is sort of a bottom-up process, where as you get experience at each level, the level above it can aggregate over those experiences and learn cases that then tell it how to perform, how to behave next time. We don't have all the levels hooked up yet. I have students who are working at each level, and our dream is to try to get everything working together. We have a couple of layers connected, but a lot of the work is done currently in individual layers. Okay, so let me sort of jump away from the technical work and just talk about, is this intelligence? If we were to build this thing and connect up all these levels, would we get intelligence? And how would we know? Right? So the interesting thing to me is that game AI, or this attempt to build interactive virtual agents, is actually a very, very old pastime. It used to look like this, right? Punch and Judy or any of these things, that's a believable agent. That's just us trying to control a puppet, trying to make it feel like a human, make it talk like a human, behave like a human, interact with you and relate to you like a human. What's changed is the technology, right? So this is a screenshot from Caneva. It's a Second Life type of environment. It's one that was done in Atlanta, so I like to use this screenshot. But it's the same kind of idea. We have puppets, us, puppeteers, that's us, controlling our avatars. Those are the puppets. They go in and they interact. Well, if we had one of these things, and let's say one of these characters was controlled by an AI, how would we know? How would we tell? In fact, what happens if you have intelligent drama management and the whole world is controlled by an AI? The world is sort of changing itself based on your experience in the world. How would we know and how would we tell? So the classic answer to that is the Turing test, right? I'll let you read that. It says, hey, Bert, ask if it has a favorite color. Where the idea is that you would, if you can't tell which of these avatars are controlled by a human and which of them is controlled by AI, then they're as intelligent as the humans are, at least in this kind of setting. So that's sort of the idea of the Turing test. If you can't tell the difference, they're intelligent, right? There of course, counters to this. You all seen the Chinese room argument, right? A few nods, a few shakes. So in a nutshell, the idea is that that's supposed to be either you or I or one of us who doesn't speak Chinese. I don't. With a massive rule book, here's somebody talking to us in Chinese. They feed in symbols. We look up the rule book, and the rule book tells us what to say back in Chinese, and we produce Chinese. From the outside, it looks like we're speaking in Chinese. We understand Chinese. But there's no understanding here. I don't know Chinese. And surely 4 walls and some paper doesn't understand Chinese. And so the argument is, well, even if you could fake you into thinking that that character is human, inside of it is just a bunch of rules. It's just a bunch of able code or some other kind of code. It's like a big Chinese rule book. My favorite counter response to that is Drew McDermott's. There are actually lots of arguments against the Chinese room argument, which is the sense that I think computer scientists understand that it isn't the set of rules that understands anything, just like it isn't a bunch of symbols on marks on a piece of paper, which encodes the quicksort algorithm that knows how to sort arrays. It's when you run the algorithm, you create a process, and the process has in it the knowledge to sort an array, or in this case, to understand Chinese, or to play a game, or to interact with you. So it's a fallacy to say that the room doesn't understand Chinese. It's a misdirection, because it isn't the room, it's the process that's being created, where the intelligence really lies. Anyway, so that people interested in philosophy, that's so fun stuff to think about. OK, so let me just close with my contact information and take questions. Charlie.
So let me ask about the perception of situation. Oh, whoops. So let me ask about the perception of situations in all the various different levels that you've talked about. So clearly at the very low level of action selection, your 2 dimensions are probably things like position or something like that, where it's very easy to tell, have a distance metric. When you get up to the top with partial plans, it's much harder to talk about what a distance metric would look like.
Right.
So since a lot of case-based reasoning involves identifying cases which are similar but not the same, what's your general approach to distance metrics along this wide axis of approaches?
Right. That's a great question. So so the basic idea behind case-based reasoning is you've got some new situation. It's characterized using some descriptors. It could be low-level descriptors like position. It could be very high-level strategic descriptors. And you have to find cases that have similar descriptors in them that then allow you to sort of replicate or adapt what you did in the past. And what we do is we have to develop similarity metrics. We have to look at a higher level, when you have these strategic structures, they look like hierarchical task networks or graphs. We have to do sort of partial graph matching between, and to look for sort of graph structures that look similar and have similar ontological elements in them. So we would develop an ontology or a vocabulary that describes a domain that then says, OK, these are all sort of, examples of this kind of attack or that kind of defense or this kind of personality, and look for distances in sort of a classic AI sense. In fact, this is a good time to plug Anthony's dissertation work. Anthony did some really interesting work on a system called Nicole, which was in some sense solving that distance metric problem inside of a case-based planner. The idea was that we would build a semantic memory, a semantic network. Also in psychology, it's called an associative memory, that recorded all of your experiences that were interconnected to each other via conceptual links, which is sort of an abstraction of how human memory works. When you were in a new situation, the new situation would then activate certain concepts in your semantic memory. Those concepts would then spread activation out to other concepts like them, and through the spreading activation process would then trigger, at the intersections of the spreading activation, would trigger prior memories that would then hold lessons for you. That's one way to sort of implement conceptual distance metrics. But there are other approaches as well in the case-based reasoning literature. There are things like case retrieval nets, which are sort of an approximation extension of a semantic memory idea. There are things like fish and shrink, which is an algorithm for the way that algorithm works is you probe into a case memory using the cues you have And then from there, you walk to nearest neighbors instead of trying to do a nearest neighbor search of everything. Walk to nearest neighbors in sort of a heuristic algorithm, trying to find things that are a little more like what you've seen. But all of this relies on having a good conceptual network, conceptual memory of concepts and relationships between them. Not unlike what you might do for example, in information retrieval problems, which I've also done work in my group, where when you want to go beyond this keyword matching, you then have to connect words in a document or in a query back to concepts, and then use conceptual connections between them to find good matches. So we're sort of doing the strategic or planning equivalent of that. That's a great question. Yeah.
So just to follow up on that second, one of the other things about the work that Ashwin and I did in Nicole was using context beyond whatever you're probing with a query, like
right.
the trace, to reweight the links in the network, so you could have the same query having a different ranking at different times depending on the agent's context. And we've had some evidence that was a pretty good thing to do, and we're still working on it.
Right.
So my question is, did you have any success working with the commercial companies on the real new games?
I think it depends on what you mean by success. They're hiring my students. EA is, for example. But mostly not. Mostly not. And my sense is that I get interest from them. And we get, I actually had one of my papers got blogged about by some game developers, and there's a whole argument about whether this thing would work or not in a real game, and so forth, which is kind of interesting to get their attention. We hit a couple of snags. One, I think the biggest bottleneck right now is that most of the CPU in a game is reserved for the graphics, which is very CPU intensive. We get very, very little CPU for the AI, and what works within that limited amount of time is really just quick scripted algorithms. We also just hit a lot of this stuff. I think is not really ready for prime time. It's still very much in research phase. Although some of the results we are getting now, I think, would be good enough to transition into a production environment if we found the right collaborators. So I'm starting to look now for people who want to work on this and make that transition across into commercial games. If you know of any, then be happy to talk with them.
Actually, I know the problem for both sides. So I worked on game AI on my university, and then I'm currently working at Google. But before that, I was at a games company, and it's really hard, nearly impossible to do something more than just scripts, because there are drives for delivery, it must be stable, everything, and nobody is really interested in creating better behavior. It's because it's not the main focus, so that's why I'm asking.
Right.
It's very hard to.
That's right, and there are the delivery pressures and the budget constraints and so forth as well. So you're right, and it's still, even with these techniques, it's still a huge engineering problem to build these AIs. And so it adds complexity.
One other issue that you run into with game AI is that a lot of the techniques that you're talking about involve learning, which scares the heck out of the testing departments of a lot of gaming companies. And I've heard many people say that in the game AI talks at the Game Developers Conference.
That's a good point. I have heard that as well, because if the game is going to learn, it gets unpredictable. It's going to do something different from what you programmed it to do.
Absolutely, I was just going to mention that. But also, in addition to this, have you done any work on limiting the resources that the AI actually takes, like in terms of memory, in terms of CPU time? Because a lot of the time in game AI, if you're going to take all of that sensory input and learn from it, you have to have a reasonably high resolution. And a lot of games, you can't do that, because that might involve ray casting to every single other agent in the world or different entities within the world, and that just is not viable. So are you going to think about pursuing that in the research? Or?
That's a good question. I have not pursued that line in my own work. There are people in AI working on those types of algorithms. either resource limited, memory limited. There are also what are known as anytime algorithms, where the system is allowed to do what it needs to do, but it has to produce a result on demand. So as soon as time's up, you have to have something available. But in my work, I haven't looked at those kinds of constraints.
Anyone else? So on the resource issue, I have noticed a lot of people in the game AI community, once an algorithm, they know what they need to do, there's often a way to come up with a set of clever tricks that make it deployable and scalable if you can specify what has to be done. So I think, as Ashwin was saying, if you know, a lot of this stuff is from a game AI developer's perspective at an earlier stage, but as the algorithms become more mature and the work becomes more, the results become more, you know, replicated and reliable, there are going to be things that people can take advantage of, and they'll find a way to make it work. So.
Yeah, there's actually a nice example of a company that was formed recently. It's called AI Live or AI.live. You've seen it. They're using techniques somewhat similar to some of the ones I use at the lower levels of the stack to learn strategic behaviors for games. And you demonstrate the behavior using a controller, Wii controller, whatever. The system sort of captures that and builds the scripts autonomously so that you don't have to program them. And they seem to be having some success. They came out of, I think some of them came out of Ken Forbes's group and a couple of other research groups and transitioned their technology. So I think you're right, Anthony. I think some of this stuff is starting to get to where it is deployable. And some is still in La La Land. You know, it's going to take some years.
It's just to comment on that, it's just funny, the method you described for learning, like taking a number of sensory inputs and then analyzing that data using an algorithm and then, you know, building behaviors out of that. That effectively is what a lot of AI programmers will do, right? They'll sit there, they'll run their game, they'll trace the data, look at the output and kind of figure out, okay, I need to build this set of behaviors to make this work, you know, work well for me. So I just find that interesting. But that's more of a deterministic way of producing reliable AI rather than your method, where potentially you could end up with behaviors that you don't want to happen in the game.
Right.
Okay.
Yeah, one of our ideas for the learning by demonstration work was that this could be a useful tool for game developers. In order to, if you wanted to build an AI, you could go play the game using a kind of strategy you wanted the system to learn. It would capture that in a script and play it back for you, and then you could go tweak it and get it perfect, as opposed to sort of writing everything from scratch.
The edge cases that could potentially happen in the script, right?
That's
I mean,
right.
that's the problem. There are always edge cases in these
Right.
in these situations. Like, for example, one guy I used to work with, he played around with flying AI, like aircraft that fly around and shoot at you and all this sort of thing. But he worked on learning procedures as well. But every once in a while, there'd be edge cases where it would just decide to crash, or it would decide to fly into a mountain. Right. And those are the sort of things that you really don't want the end consumer to see, because they'll go, you know, you suck. This game sucks. You know.
Right.
So I don't know.
That's point's well taken.
So you said earlier you made the point that the state space is very large, so you can't just throw machine learning at the problem. But then your approach is to show your many layered AI at every level of which you've made an abstraction of the state space from the level below. So of course you're reducing the size of the state space at every level. So having made your abstractions, why don't you just throw machine learning at the problem at every level?
So is the abstracted state space small enough now?
So at the planning level, like at the top, like at the level of like plans, for example, right? You have, let's say, a limited set of actions, planning actions. It's 10 or 20 or 30 or however many, but that's a lot smaller than working in like XY coordinate space, right?
So yes and no. So we are in some sense throwing machine learning at the problem, but we are doing it lazily. The problem with pre-training everything is that even if your state space and your action space are somewhat limited, games extend temporally over many, many cycles. And to play sort of all possible combinations of all the games and try to capture everything up in advance is still a huge computational problem. Right? So one of the ways that learning by demonstration helps, for example, is if I watch you play, I'm getting sort of a path, and I can explore some of the region around that particular path, whereas there might be another path over here I'm not going to explore because it just might be completely off the wall. Right? The system would have no way of knowing which one it wants to explore until it actually sees a demonstration by an expert, another player, in that direction. So in some sense, it's using experience to guide the exploration process in productive directions.
So it seems like when a human starts playing a game like Warcraft, he brings a lot to the game that he doesn't necessarily learn there, like basic algebra to figure out what he can purchase with his available resources. And it might not be effective to try to train the game to learn that sort of thing within the game.
Right. That's a good point. So there is, I think there is a lot of stuff that we bring to bear to the game that potentially could be learnable, but may not be productive to spend learning energy on that. Right, and so you're right. The game playing agents do have a lot of stuff built in already, which is all the stuff we don't want them to learn, and we're trying to focus on we're trying to sort of stay focused on what we think it would be productive for the game AI to learn. Mm-hmm. So, for example, one of the things we are looking at is if you take a game where you have a large state space, there are many possible combinations and derivations of that state space that could yield sort of high-level abstractions. Not all of them are equally useful. How would a system couldn't compute all of the deeper or more abstract features out of the surface-level features, because that would be computationally too expensive. Now, we could knowledge engineer a set of features that we would like the system to use, which is what we've been doing thus far. But I have a student now looking at, could a system actually learn which particular abstractions are worth learning through trial and error? Right.
Anyone else? All right, well, thank you very much.
Thank you.